Hi, everyone. Welcome to this educational program brought to you by the Light Brigade and hosted by Lightwave Online. My name is Larry Johnson, and I'm going to be presenting the session today. I am the director and founder of the Light Brigade, and I'd like to thank Stephen Hardy and his entire team for making this venue available. This is the 10th of a series of webinars that are based on comprehensive fiber training programs, and we hope that they'll enlighten you about key topics and concerns that you may have. So the speaker again is going to be myself, and so if we go to the next slide, there's some housekeeping issues, and so one presentation is going to be available, as you can read on screen, and that after we conclude today. And we do have the Ask Question box over to the left side. And we encourage you to ask questions. I hope to cover most of the topics today, but there's always those that are specific to your application and your needs. And we do want to present those. At the end of the session, I'll also give you my email address so that if there's a personal question that you want one-on-one as well, we can do it. However, the questions that are going to be asked, the other viewers will not be able to see who these questions came from. So anyway, feel free to type in that question, click the submission button to send the question along, and I'll be answering those questions at the end of the presentation. So if you have also one more issue, if you have a technical support issue with the webcast, you can alert the technical support staff through this question box as well. Sometimes it's audio or video or so forth. And one question that we get constantly is whether a copy of the presentation is available for download. And we don't make the presentation available because there is some proprietary information, some diagrams and photos and graphics that are copyrighted by different entities and so there's some legal issues there. But you will be able to take a look at the session again, and you can go to Lightwave Online educational web page and view the presentation in its entirety on demand as often as you want. So with that, let's begin. Okay, so a little bit about the company. I don't think I have to read this. I think everybody can see it for themselves, but we do take pride in our courses, and that our staff, our content, and equipment. We're constantly updating material, doing research from standards, but we're also listening to our customers, and which are you, and so keep in touch with us. We love to hear from you. So the introduction here is what we're going to talk about is the test equipment that's used in fiber to the X testing and troubleshooting. We're going to talk about the test disciplines, including the testing, the troubleshooting, maintenance, and restoration. These are going to be pointed more to the point-to-point type systems, such as active Ethernet, but also the PON systems, which are point-to-multipoint, and again, troubleshooting. So the test equipment is primarily based on the physical plant or outside plant test equipment. We're going to deal with attenuation, which is the optical time domain reflectometers, the most commonly used piece of test equipment to get a signature on a trace to measure attenuation, reflection, but also the optical power meter, and there's variations of those, and as part of an optical loss test set, the light source and the power meter as a set. We're also going to talk about reflection, whether it's going to be optical return loss or return loss known as reflectance in the session. And we're going to, of course, have to address power issues, therefore using the power meter. And for those doing testing and troubleshooting, anytime that we connect or disconnect, there's a potential for contamination or damage. So the surface quality of your connector is critical for the success of the fiber link and therefore the bit error rate and the quality of signal. And that's the inspection scope. So here we see a photograph of someone doing an acceptance test on a reel of cable, and you can see a cable table, an OTDR, a reusable mechanical splice, and a variety of tools. And this happens, looks like it's a nice day, and if you've ever done acceptance testing, when you get a nice sunny day and you can work outside, this is the better part, because most of the time in emergency restorations you'll find that the weather's not that good, and so it's nice when you can wear short sleeves and work in a nice environment. Anyway, so the different roles that apply for the testing is when cables come in from the manufacturer, and to do it, perform an acceptance test, making sure that they meet the criteria specified by engineering, and then purchase through the purchasing department, and making sure they meet specifications. Once the cable's installed, we want to make sure that it was installed properly, and so that's testing for span continuity, but also for making sure that we didn't induce any macro or micro bends during the installation. Once the different spans are connected, then we measure the splice, the distance to those splices, and the attenuation through them, normally at two wavelengths, 1310 nanometers and 1550 nanometers. At that point, then if you're dealing with a PON network, then there's a splitter, and so do we isolate the splitter attenuation, and we'll cover some signatures on these as well as we go later. And then there's the two types of reflectance testing. There's optical return loss, normally specified as ORL, which is the sum of all the reflections in a span. And then there's the reflectance, many times called out as return loss, which is an individual component that's being tested for reflectance. And then when there should be one more bullet here, and it would be the end-to-end optical loss test, and that could be done with a light source and power meter, or it could also be done with an OTDR, but the optical loss test set's more accurate for doing a final test. And then if we move into the maintenance or restoration mode, then it's critical to not only identify where the fault is, but the extent of the fault, and we'll spend a little more time on that, as well as being able to recognize the OTDR signatures. Okay. So the system test points, though, or in these type systems could vary whether it's fiber to the building or fiber to the home. And so for one thing, we want to, wherever we're going to test, we're going to need a fiber optic connector. So we have patch panels. We could have connector ports at splitters. Those could be housed in fiber distribution hubs, fiber access terminals. They could be located at multi-port service terminals and that. But wherever there's a fiber connector gives us an access point for testing for optical power or access for different devices. But we still have to determine when and where we're going to use the different equipment. Stepping down to the third bullet, active Ethernet. Normally these are point-to-point networks, and that so from the central office or head in, if you're a cable TV operator, to the cabinet and the outside plant. That would be a simple, traditional transmit and receive two fibers. Could be one bidirectionally, but most of the time it's transmit on one, receive on another. And then again on your drop cables from the powered cabinet to the individual subscriber. So those are different segments in that of an active Ethernet link. On the other case, the outside plant end-to-end, our goal as far as troubleshooting is going to always be to isolate the segment at fault. Okay, so one thing that I've recommended for years now is that from a design standpoint is to use a spreadsheet and develop a not-to-exceed chart. And what this does is it identifies the losses that are expected in a span. And they're extremely valuable in acceptance testing of a span and any troubleshooting, because if you have, for example, a contractor that's going to do the installation for you, you can give them the spreadsheet and you can say, here's your not-to-exceed numbers. And if you look at the last bullet, it says they're based on the length of the fiber, the type of the fiber, the wavelength. For example, fiber to the home network specify an upstream attenuation level of 0.4 dB per kilometer at 1310 nanometers, but also downstream at 0.3 dB per kilometer at 1490 or 1550 nanometers. So you would, based on the length and that, you would determine what the maximum fiber loss is going to be. And then your splices, we recommend using the Telcordia GR20 value of 0.1 dB per splice, frankly, because the ITU G671 standard specifies a 0.3 dB value, and we just feel that 0.3 dB value is too high of a loss for an outside plant splice. And that, so we recommend the Telcordia GR20 instead. Connection splices are specified as 0.5 dB per connection, again specified by the ITU's G.671 standard, which is the fiber optic passive devices standard. And the splitter attenuation, we're going to show you another chart that gives you the values you should be using versus the theoretical values. But what you do is you put all these together, the number of splices, number of connections, the fiber length, and the splitter attenuation. You end up with a value for any segment, whether it's from the central office to a splitter cabinet or for just all the way from an OLT to an ONT. But always customize these to your needs, and they do account for your attenuation. Okay. So here's an example of a not to exceed attenuation value chart just for the optical splitters. And most of the time when someone says a 1x2 split's 3 dB, that's true theoretically. It's not true for what actually is going to occur. And the G.671 passive devices standard gives minimum and maximum values for those optical splitters, but the average numbers are the ones that are shown on this chart. And these are the types of information that we have in our various certified fiber to the home professional courses, our outside plant design courses, and our online CFHP courses. But it's very important that we use practical values, not theoretical values, because the theoretical values, whoever's installing is never going to meet those numbers. But these are the actual average numbers that are in the standard and should be used. Because this is looking at a PON situation with an optical splitter, the distance is never to exceed 20 kilometers. The wavelength is 1310 and 1550 nanometers. Very rarely, even though 1490 nanometers is used downstream in the basic band, most fiber attenuation values you use the 1550 value instead. And again, I gave you the splice values prior for the number of the splices and the connectors. Okay, stepping over to reflection testing, two different types of reflections. Fresnel reflections directly affect the operation of a laser and therefore will affect the signal quality as bit error rate, but also as a result of that, latency in systems. Connectors are the major cause, and the largest of those is the connector that's closest to the transmitter, and that because it has the highest amount of power being reflected back into the laser port, and once it affects the laser, then all of a sudden the lasing operation is affected, and if we end up having to resend the information because of that, then latency is the effect. So, but there's other causes besides the front-end cross-connect panel, for example. It could be open ports at a splitter cabinet, and that, so say it's a 1x32 splitter, and you're only using 16 of them, and that means you've got 16 open ports, and that so you can either link these up and cross-connect through, or use a device called an optical terminator, which is a dead-ended plug that has to match the polish type of the connector, and most fiber to the X systems use the angled physical contact, or APC, end face. And that, so any open end face can create reflections, and laser transmitters are affected by these. But also cleanliness affects reflectance too. Isopropyl alcohol directly is one of the worst solutions. It's good for cleaning the outside of a fiber before splicing, but for optical end faces and connectors, we should be using other appropriate cleaning materials that do not affect reflectance. And again, the term ORL, it's the sum of all reflections, which is the Rayleigh reflections intrinsic to the optical fibers themselves, and the Fresnel reflections caused by abrupt changes in the optics, connectors of which are the major cause. And remember, the term reflectance is the term for an individual component. So if you're looking at, say, a connector on a patch cord, it may be rated as an SC UPC connector, and the rating would be 55 dB. That's a reflectance value. That's an individual part. But an ORL value for a system could be 32 dB, but that's the sum of all the reflectance. However, if ORL, if you do not meet the ORL value, it's an individual reflectance that's causing the problem. So once you don't meet ORL values, then start testing for reflectance and identify which part it is. Okay? So let's start off with the OTDR and when is it used. So normally before, during, and after the installation of a fiber span. So you're testing the cable to make sure that it meets your specification. You could be monitoring an installation or a restoration as it occurs. And then after the installation to make sure that the cable was installed properly without extra losses induced by macro or micro bends. It also is used to confirm splice attenuation during splicing of spans, feeder to distribution, distribution to drop. Could be the entire connected span end to end. And also, and we're going to talk about this more, is the specific characteristics through optical splitters themselves. And of course, one of the major causes for buying an OTDR is for maintenance and troubleshooting and restoration. So we have to make sure we know how to use an OTDR and select the right unit for it. So where is it used? Well, it'd be preferable if we could always use it at our hub sites, and that where the technicians can be warm, they got power available and that, and they can test a span. However, this gets very difficult, as we're going to see with different types of outages. And so sometimes truck rolls are going to be required to take the OTDR outside the hub site instead. Okay, so some of the key issues that you need to address on an OTDR when you select them. We're going to address some of these further on, so right from this point we'll just hit some of the key bullets. And that's one of them is the dynamic range. In other words, how far can a laser pulse be transmitted through the OTDR and then again get a return signal that which we can analyze accurately. And that another one is the dead zone, and this is an effect of the reflectance of the connector, the rise and fall times of the electronics, the optics such as the laser and the photodetector, and the pulse width or the time duration that the laser is actually on. For example, if we want to find a fault in someone's front yard 20 kilometers from our test location, we're going to be extremely concerned with the pulse width of that OTDR. So we'll talk about these later. And then again, because it's a test and measurement equipment, we want to be able to store traces, and not only store them, but we want to recall them into the future, and we'd like to overlay them so that we can visually see what has changed and where it's changed since we did our initial testing and documentation on that. So good comparisons make it easy to find and locate faults. And always remember that these instruments should be suited to your application and requirement. For example, OTDRs that you may have that are used for testing long spans, say an 80 or 100 kilometer span, is really good for the amount of power that they have because of the attenuation in that span. But we need an instrument that we can see in a PON network specifically for a short span, 20 kilometers, but we need a very high resolution to be able to find a fault after a splitter or even worse in between splitters and that. So different types of instruments. So we're going to have to compromise on some of the specifications, and we'll talk about these. But the key point is going to be that we're going to use the OTDR to measure attenuation, optical return loss, and reflectance, and pay close attention to this on your OTDR because a lot of technicians, actually I would say the majority of them, really do not know the difference between ORL and reflectance and how to test and make sure that they set the OTDR's menu to make sure they're identifying the right task and tasks that they're to perform. And of course the other task that OTDRs do is measure length. So here's an example of just a graphic of an OTDR pulse, basically. And what from the graphic, you see anywhere on the vertical scale is always attenuation. The horizontal scale is always distance. So it's a case of saying we have a pulse, and if we turn a laser on for a time sequence, how far did light travel in that time sequence? And if we say, well, we turn it on for 1 second, that pulse is going to be 186,000 miles per second, 299,000 kilometers per second. So obviously we're we're modulating the laser much faster, and that so that we can see accurately very close in. So if you're looking at OTDRs to specify, one of the things that you need to look for is what is the dead zone, and what is the pulse width, and then what is the effective dead zone for a reflective event and a non-reflective event. And then at the same time, rather, if I went out to buy a car, I would always go and take it for a test drive. If I'm going to buy an OTDR, I really want to see it and how I'm going to use it. Now, most OTDR manufacturers have the ability to send an instrument to you or have a demonstration performed. But if you do have this occur, and that, always set up what your expectations are before the OTDR comes in and says, well, we're going to use this to test a point-to-point active Ethernet system, or we're going to use it to test a PON system, or we're going to use it to test a long-range system, or in an enterprise network. But set up your test and say, let's go through and let's do some tests and see how the instrument works and what it does. I've just seen too many times where somebody comes in and they show an OTDR in a meeting room, but you really didn't test it on your network, which is how you're going to use it. And it's, like I said, on buying a car, you're going to take the car and take it for a test drive. You're going to take it on the highway and the freeway and get a feel for it. That's what you should be doing with any high capital expense test equipment. Make sure it meets your purposes. So on the first bullet on dynamic range, there's 2 points here that I want to address. One is there's lower cost point-to-point OTDRs, normally with a dynamic range of about 30 to 35 dB. And what they're designed for is just that, between points, and that where there's no high losses caused by the optical splitters. The other version would be a higher cost OTDR, which would normally be in the 40 to 50 dB dynamic range category. And this will allow you to account for, say, a 1x32 splitter with an average attenuation value of 15.8 dB, plus your point-to-point losses. So you're paying for dynamic range. So you really need to pay attention to the two variations and whether you're going to test through a splitter or not. The other one is if we're measuring 20 kilometers out and we go through an optical splitter, we also want to have a very short pulse width, but we want a high degree of sensitivity or dynamic range. And that we're on a normal, say, extreme long-haul system, where normally you increase the pulse width as you go longer spans. In this case, we don't want to increase the pulse width. But we also want to have an OTDR that gives us more data points and that. So, today it's not uncommon to get an OTDR with 32,000 or 64,000 or 128,000 data points. And if you look at that over 20 kilometers, it tells you how often the fiber is being sampled by the instrument. And that means you're going to have higher resolution between faults. But you're going to have to marry the resolution and sampling to the pulse width of the instrument and the dynamic range. All those are interrelated. And that, so, how far an OTDR can see is going to be based on whether it's a point-to-point or a point-to-multipoint event, and then how reflective an event can the OTDR resolve. So in this chart, what I wanted to do was just kind of show a perspective of how you can put these together. So here's a basic outside plant map for the central office on the left side. We have our connection point internal, and that where we could hook up an OTDR. But if you look at the different events, first one is there's an entrance enclosure inside the central office. And if you're going to try to measure this splice at this point, you're going to be dealing with an extremely short pulse width to do so. And most of the time, these type of events cannot be located with an OTDR. But again, if you're going to set up a test, you say, I want to be able to test the splices at the optical entrance enclosure from our fiber management bay. Identify it. The outside plant closure, where the outside plant cables come into the inside plant, could be another option. Should be a little further removed, but normally they're right outside the CO, relatively close. And at this point, we're testing with a very short pulse, and that possibly a medium pulse width, and that depending on the distance. As we go further down the span, here we transition to an aerial plant, and we have an aerial closure. So again, test with a shorter or medium pulse width. We don't need the dynamic range to go long distance yet. But then as we do go down the span, now we transition back to the underground. And in this case, we're transitioning from a feeder into a feeder closure and then doing a transition to a distribution point. So in this, we can go with a shorter pulse width, maybe with high averaging, or test with a medium. Now, the difference between the two closures, and this is for those doing design work, and that just what you can do is you can keep your feeder isolated into a primary closure, and then you do a mid-entry and you drop to a secondary closure, and all your local terminations or drops are done from that secondary. In other words, don't access a feeder cable just to do fiber to the home drops. You want to isolate this and protect it as much as possible. But what happens here is to test between these two closures, you have splices relatively close together. So again, one of them showing test with a short pulse width with high averaging, the other saying just test with a medium pulse width if we're just passing through. And again, the drop, the upper closure where we're dropping to a splitter cabinet, a fiber distribution hub in this case, allows us to isolate that splice. Further down, we see where we transition to the final drop cables from distribution cables, and whether this is through a multi-port service terminal or a fiber access terminal, or just a drop cable from a fiber distribution hub. This is normally dealing with a short pulse width with very high averaging, and that to suppress as much noise as we can and get a good trace. Okay, so a little different now is that was talking about how to get the measurement and how to set up your OTDR for using pulse widths and averaging. So now to go to measuring optical return loss and reflectance, is always remember that you're limited by the dead zone and the pulse width of the instrument. You always have to match the connector type, the fiber type, and the polish. So if it's a single mode SC/APC connection, it's telling us that it's a single mode fiber. It's the physical connector, the SC, and then the type of polish. These also, anytime you're measuring reflectance or return loss, cleanliness is critical, and using the right materials. And that means not only testing the plug that you're working with, but the mating side as well. And so again, reflectance is always going to be a component, optical return loss a system. Now what you are seeing on the screen is an OTDR linked up to a dead zone box. Now there's three fiber optic test procedures that define that a dead zone box, sometimes they're called pulse suppressors, but they actually don't suppress the pulse. The pulse always stays the same, so I like dead zone box as a better term. Anyway, three fiber optic test procedures define that a dead zone box should be 20 times the minimum pulse width of an OTDR. Now, because most manufacturers, they know their pulse widths, but most users actually don't, it's normally easier to buy dead zone boxes in 500-meter or 1 kilometer spans of fiber. And what this does is it pushes that first connector out. We're just going to say 1 kilometer at this point. So from the OTDR's perspective, the first span would be 1 kilometer. And now you would be able to get a signature where we could measure the attenuation and the reflectance of that connection because it's not buried in the dead zone of the OTDRs and that from the launch site. Now, if you want, you could also put one of these at the far end, and so then you isolate the far end connector and are able to measure reflectance and attenuation as well. Another way without using two dead zone boxes is using one on the front end and use an optical terminator on the far end, but the optical terminator will only allow you to measure the reflectance. It won't allow you to measure the attenuation as well. So here's an example of an OTDR shot. And in this case, if we look at the top screen, I don't know how easy it is to read on your presentation, but the first is the reflectance at the start of the OTDR test. The second is the end reflection. In this case, it's 21,664 meters. But the reflectance level's 59.33 dB. So what that tells me is, number one, that it's an extremely low reflectance value. It is a fiber in with it. We know in this case it was a fiber in with a UPC connection, but normally this would show up as a very high reflectance, even though the UPC is rated between 55 and 60 dB. So I'm meeting spec, but there's an optical terminator that's been cleaned and plugged into that UPC to get this level, and this is the level that we would document. And again, an optical terminator, and these cost about a few dollars, plus or minus 10, plus or minus a few dollars on it. So they're not that expensive, and that, but you do need to make sure they're always cleaned, and you do the test, and then you move to the next connector, do a reflectance test, and so forth. But there is a slight Fresnel reflection. You can see the little tip right on the end there where it does increase. If I disconnected that terminator, it would be a much higher reflectance, and the final measurement would show probably in the 20 to 30 dB range, just because it's a glass-to-air option at that point. Okay, so here's another trace. This is showing a non-reflective OTDR signature. Most commonly, you see them in fusion splicers, because fusion splicers are getting so good now, plus the fiber tolerances from the manufacturers are just excellent. So it's not common to flatline a splice, and so you know that you have a splice point, but there's virtually no loss showing through these. So but it is non-reflective on fusion splicers. Mechanical, on the other case, would be a Fresnel reflection it would be similar to what we saw before with a UPC polish with a terminator, but in the 50 to 60 dB range normally. But other non-reflective signatures are caused by macro bends and micro bends, macro caused by bend radius, and micro caused by pinching effects. Some other non-reflective events can be caused at a fiber end. For example, if the fiber's broken and it's fractured where the light's not reflected back to the transmitter, then that would show as a non-reflective. On the other side, extreme macro bends do the same. They don't allow light to pass back or return. So, excuse me for a second. So if it's extreme macro bend, we have the case where you don't get a reflection from it. Others are, of course, if the cable's underground and there's water in the ground or so, if the cable's broken, then water intrudes in and it tends to absorb the light, and it's closer to the index refraction of glass than it is to air, so it could cause a non-reflective signature. And for those that have older cables that use the icky pick in the cables, there's a good chance that the cable gel got around the fibers and again created a non-reflective situation. So here on the chart you can see where the actual non-reflection would show. Now this signature can also be very common though in looking at say a 1x32 optical splitter in one location where we have an extreme attenuation, roughly 15 to 16 dB, but then we'd see the drop splices, the drop terminations from that, and we'll show that coming up in a little while. So let's move on. Okay, so point-to-point testing, what we're trying to do here is making sure that we meet the optical specifications on the physical layer, but there's also the network end-to-end testing that occurs that it will guarantee the quality of signal and the bit error rate. And in this case, there's two different standards, the RFC 2544, which is based on IP testing, and this has been around for many years. But there's a newer one, and I'm sorry I didn't list this on the slide, but it's a ITU-T and then space, and then it's Y.1564. And this standard is written from the service provider's perspective versus a manufacturer or the legacy Ethernet perspective. And at the end of the session, I'll give everybody my email address, and so if you want information on this or a reminder, just email me and I can get that to you. But what we're looking for is information such as throughput, burst rate, frame losses, latency from a full system perspective, whereas on the physical layer, we're looking at attenuation and reflection and distances. And basically, we can segment this, as you see in the graphic, that we have a feeder cable going either to a splice point or an active Ethernet example, a powered cabinet, and then we have individual drops. So it's saying where's the problem? What equipment should we use? And preferably, we'd like to test this without a truck roll to save money. Okay. Testing PON systems gets more technical and more difficult and requires more expertise. I really love it in our fiber to the home installation and technician courses where we build a PON network, we test through the splitters, we teach the reflection testing, all these elements, because it really opens your eyes when you're right there in front of it with the equipment and you're able to see what happens even on a single port reflectance issue and that as well. So what we're looking at here is the standard 3 wavelengths, the 1310, which is your upstream from your subscriber back to the service provider, your 1490 nanometer downstream basic band, and your 1550 nanometers used for RF overlay for analog video, but it could be digital. And then we're looking at testing for reflectance and optical return loss again. And even with a PON system, there's still point-to-point segments, the feeder segment, the distribution segment, and the drop segment, and that. So whether you want to test those individually or if you want to test them as a point-to-multi-point span, you can do so. It's a case, especially when we come to troubleshooting, we really want to isolate the segment on where the fault is, and the alarms that we're going to get from the ONTs are going to really assist us in when to test or where to test from, and that so that we don't drop other users and that. But the goal is to identify the location and the type of fault soon with the best expediency and the least impact. We also have to address that for those looking ahead from legacy PON systems, that these standard 3 wavelengths are going to change for your upstream attenuation and values. For example, upstream is not going to be just 1310 plus or minus 50 nanometers. It's going to be specifically 1260 to 1280 nanometers. And then the downstream is going to be using the 1577 nanometer wavelength instead. And this applies to 10G PON and 10GE PON. But the RFOG uses an option of either 1310 upstream or 1610 nanometer upstream, and that. But the downstream would still be the 1550 nanometer. Okay, so one thing on test reports and documentation, making sure you have a header that describes the date, the direction of the test, the operator who's doing the test, the wavelengths tested. Basically, you want the information of the documentation so that someone 2 years from now can go back, look at that documentation, and duplicate the test. And so that's what we're talking about, header. The other one is pay attention to fiber numbers and color codes, because you will transition. The more you do mid-entries and the more you use splitters, the color codes aren't always going to match up in that. And then again, there's bidirectional testing, and there's optical return loss testing. Okay, so let's take a look at OTDR testing of splitters. I'm going to take a slight second break here so I can take a sip of water. Much better. So anyway, splitter losses are always high when compared to splice losses, and most OTDRs have defaults that you can set menus, and most OTDRs are set for a 3 dB default. And that, but you may have set them for a 0.5 to look for any type of connection loss or splice loss. But remember that if you're going to be testing through splitters, you're going to have to change those defaults for the attenuation value of the splitters that you're going to be using. And resolution's key, so that you can get the least amount of noise and the best trace, which means averaging. And that, making sure you have the right dynamic range, especially going through splitters, because if you're trying to use a 30 dB OTDR and you're hitting a 1x32 splitter, you're going to run out of dynamic range. And the signatures that you're going to see are going to be ones that you need to understand what they are. You need to interpret them, and you need to be able to measure both reflection and non-reflection values. And then drop cables, and we'll show an example of this, with equal splits have to be different lengths. The OTDR cannot differentiate from one to another. And on this chart here, you see an example of this. So, where, the question here is where's the splitter? And that's where you see the first linear line, then it drops down about 3 to 4 dB. and then all of a sudden you get a noisier trace. You can see as we're getting closer to the noise floor, and that more noisier it is. And this is where dynamic range is very important on an OTDR. The more dynamic range you have, the less noise you have, and therefore it's easier to measure attenuation in particular. And then in this case, we show 4 different drop cables. So in this span, we're using a 1x4 splitter. And each of the drop cables were different lengths, and there was enough difference in the lengths where the OTDR could differentiate these from each other. We still don't know which drop cable goes to which home, but the alarms would tell us that if we needed to know this, and I'll talk about that. We don't want to just automatically throw an OTDR on a fiber span and then drop 32 subscribers. So, but anyway, you can see the pulse of the instrument. You can see the rise time as it comes from the trace line up to the peak and that, and then you see a duration that's on, then you start seeing it tailing back off to the bottom and that. So you're seeing rise and fall time. You're also seeing pulse width occurring. And if the distance is great enough between the 2 events, then we can differentiate the exact loss between them. And that the best thing is have an OTDR with a short enough pulse width, and normally we're looking at 5 nanoseconds to be able to make these measurements. But if the drop cables are the same lengths, they're just going to lay over each other, and you're not going to see the difference from one to another, and that which makes it a little more difficult. So we'll talk about testing with visual light sources later and that. But the drop cables is real key. Obviously, the drop cable spans are shorter. It means more training, more expertise on the operator of the OTDR, and it also means selecting the right OTDR. And that, so the OTDR with higher dynamic range is going to be required for testing through an optical splitter. And that, you may be able to defer by using standard optical loss testing. For example, if you can test a point-to-point segment from the optical line terminal to the splitter location as a point-to-point network, identify that loss, then measure your drop cables as separate segments as well. And then if you want to take the transmit power, just using a power meter, measure the receive power at the input port of a splitter cabinet, and then measure the output port with the power meter. The difference in those power levels is going to be the loss through that splitter for that port combination. Pretty easy to do with a handheld instrument. And then for continuity testing, very easy just to use a visual laser. So the basic optical loss test set is a light source and power meter. The set shown is just one light source and one power meter, but you can also get them built in so that each end has transmit-receive functions. It's a case of dollars. If you want to spend more money on the equipment, you're going to find less labor, and you're going to have better equipment to do so and that. But just make sure that you're testing at the right wavelengths, and look at the waveform storage as far as the documentation and port-to-port. One of the things I like to see, too, is sometimes people make mistakes when testing. How easy is it to back up and then remeasure a trace and redocument it? So we're going to use this type of equipment for end-to-end testing. Good continuity checks. Remember, just the power meter by itself is probably the most essential piece of test equipment in fiber optics. We can measure transmit power. We can measure receive power at any point where there's a connection. And just remember, light sources have to be stabilized, and power meters have to be calibrated. 2 key points. So here we're showing testing an optical line terminal for downstream transmitter output power. And in this case, we're seeing an UPC or APC connector at the OLT. So we're measuring in dBm because it's a power measurement, and because it's normally using the basic band for downstream, this would be 1490 nanometers. If the power meters only has calibration points for 1310 and 1550, use the 1550. You're not going to be off 1/100 of a dB in value. To measure upstream power measurements from the ONT, though, we're going to need to have an inline PON power meter to be able to perform those tests, and we'll talk about it a few pages up still. But always remember to clean as well. Okay? So let's go to the ONT now. and look at it. So in this case, we can measure the downstream power level using a traditional power meter very easily, 1490, 1550. Basic band or RF overlay, and again, we're matching the connector, we're cleaning it up, but remember the key word here is that we're testing the receiver input power. Now let's go to look at measuring a ONT transmit level, and that an ONT has built-in safety precaution called the automatic power shutdown, which means that if someone disconnects the connector from the ONT, that the laser shuts down. And this is a safeguard because as much as we would like that subscribers don't go and open up their boxes and want to look at the fiber, or sometimes it could happen. We hope it never does. And even though the lasers are class 1, low power, retina safe lasers, it's still a safety precaution built in. But what it means though is if I want to measure the transmit power of that ONT, the laser just shut down, so that means I have to put an instrument in line, and you'll see from the instrument shown here that it has 2 ports on it, not 1. In other words, one of these ports has taken the downstream power from the OLT, and the second ports act as linked to the ONT. This provides a continuity, and the laser then at the ONT won't shut down, but will actually transmit. And these PON power meters allow for both upstream and downstream power measurements. And they also have other features for protocols, handshaking, how many samples and that. And so when you're looking at a power meter and you need to do bidirectional testing from the ONT, the inline function is a very important function to have. Okay. One thing on the optical loss test records or documentation is, when you have your traditional point-to-point network, you have fiber 1, fiber 2, fiber 3, and transmit and receive. You roll your jumpers at the end, and you document your attenuation, you document your power levels, and your color codes, and it's pretty simple. The difference when you're getting to a PON network, though, is all of a sudden you're going to have one OLT transmitting to up to 32, or actually in the case of GPON, you can go up to 64 optical network terminals. So take a look at the types of record keeping that manufacturers build into their test equipment. It says, okay, well, you can document and store your traces here, and then you can download those later. And that it's a lot easier than the older days where we had to handwrite all these. But it's real critical that we get the right measurements and that we ID both attenuation, wavelength, date of the test, who did the test, what direction the tests were done in, and all this information. So, but do check it. So here, now we have a network. It's been operating. And all of a sudden, the ONT, by the way, on the basically OAM and P functions, operations, administration, maintenance, and provisioning functions, sends information upstream periodically, actually every second. And it just basically just says, I'm online, this is my signature, et cetera, et cetera. But it's also an alarm function, and for any reason, whether it's a fiber cut or a power failure, that ONT will not be able to transmit that information back upstream to the OLT, then it would go into alarm. If it was only one unit, then only one ONT it would be affected and would be an alarm. However, if you had all 32 of them not communicating upstream, that means this is the only time that we can normally put an OTDR on a span and test for continuity. And that. So in this case, we could use the OTDR from the central office dedicated to that fiber, and we could look and say, do we have continuity to the splitter location? And then if we do, then we could take a look and say, because you're always looking for the common element. In this case, it would be one fiber that's feeding 32. The second element would probably be the splitter itself. And of course, here we're talking physical layer. What if it was the OLT? So in that case, we'd have the alarm in the chassis itself. but we'd use an optical power meter to compare the original transmit power going out as well. So anyway, in that case, anytime you get a full complement of outages and that dedicated to one fiber, you're looking for the OLT, the fiber, or the splitter. And the second example would be a 1x2 feeding a 1x16 on each leg. So in this case, if we only lost 16 out of 32 of the drops, our common element would be the 1x2 splitter. Well, we wouldn't want to put an OTDR on because we'd drop the other 16 subscribers in that. So in this case, you would do a truck roll to the common element, and then you'd be using your power meter, your visual laser, and that you could take an OTDR, but you probably wouldn't want to use it, because of the short spans. You're going to look for the common elements first, and so forth down the numbers. Okay, so the bottom, we hit to the active Ethernet systems, point to point. And again, if the system's down, then you could use your OTDR very easily in that. But if it's a drop between the powered cabinet and the drop cable, then we would have to do a truck roll to the location. Now, there's one other issue here. On a point-to-point PON network that's with a home run topology, the optical splitter is in the CO and that. So in other words, all your maintenance can be done. So if that's the case and we ended up having a single fiber drop, you could actually isolate the single fiber and OTDR test it from the central office down to the subscriber. You wouldn't have to do a truck roll, and that's one of the key advantages of a home run, is the fact that you can manage the system without having that OpEx cost and that for maintenance purposes. Okay. So again, going back to where do we test from, and here's an example. The homes, the ONTs are on the left side. We have three different situations here. We have a drop cable directly from the FTTH or an active Ethernet hub to the ONT, so that's a point-to-point segment. And then we have the middle one where we have a splitter cabinet going through a splice closure, and maybe that splice closure, maybe it's a rural application to where you're going down a road net and then you're doing a mid-entry or dropping a splice for a farm, for example, and that. And then the last one where we have a fiber access terminal or maybe a multi-port service terminal in between. So maybe at the FTTH we have a 1x8 splitter, and then each of the FATs would have a 1x4 splitter into it, and then service 4 different drop cables. So what we're trying to do here is isolate where the problem is. So if you're going to use an OTDR here, it's an expensive piece of equipment. Take out into the field. You're going to need extremely short pulse width on this instrument. The main thing, though, is try to isolate the fault quickly, and the first one's using the optical power meter, and so check for transmit power levels and receive power levels at any connection point compared to the past records, or what should be the power level at that point. For quick continuity checks, use the visual laser. Their range is normally good for about up to 2 kilometers. However, don't look into the light because these are Class 2 or Class 3A power levels, and that they are not retina safe. But they are good for continuity just to show that we have light from point A to point B. And if we're talking about a drop in someone's front yard, I would look for the freshly planted rose bush, trees, gardening things, and again, this comes down to your outside plant design and courses to say, if you want to protect that cable, you really want the minimum depth of burial for the National Electric Safety Code is 18 inches, or put it in Schedule 40 PVC as well at 18 inches. But either way, give a little more protection, because this is going to be the types of outages that are going to be more common in that for it. Even a drop cable for active Ethernet, again, it's a short point-to-point network, net, simple continuity testing, power meters and light sources, and that used. So, with the OTDR, though, use the 1550 nanometer wavelength to locate stresses before and after a break. So let me talk about this, for example. If you have a cut cable, auger, backhoe, tree branch, whatever, washout, the OTDR can find the end of the fiber. But sometimes it's not as easy as it's meant to sound. For example, maybe it's a non-reflective break, number one. Maybe there's water around it, so you don't know exactly where the break is. You were trying to get close geographically where we can do a truck roll and send someone out to say, okay, what equipment are we going to need, and what are we going to do to restore this? And that, so you test until you find a Fresnel reflection. Go fiber to fiber till you get a Fresnel reflection, and that set your cursor. Then test all the other fibers and make sure that the break's actually there and not at a distance from it. Maybe prior it's been stressed 50 meters before it, and that. So use your scales, use your resolution, and measure the locations. For the troubleshooting, again, during the initial installation, where is it at? The OLTS, optical loss testing, OTDR testing, service provider hub to the subscriber. Isolate the section, and it's very easy to do, and that minimize the impact here. The simplest test of all is, especially drop cables, is to use the visual fault locator. You are limited to a couple kilometers in that, but it does allow you quick testing. The other one, as it's shown here, is we have a microscope just looking at the interface of a connector, and it can be something as simple as a connector's been disconnected and remated back up, and it got contaminated in the sequence. And that fiber identifiers, again, if you're looking just to say, at what point can we isolate quickly, put the 2 kilohertz tone on from your light source, clamp on a fiber identifier, and say where the fiber is directly from the location where the potential break may be or trouble. And that. Be careful though of bend insensitive fibers because they're bend insensitive, so they may not be able to show this as well. And again, as we showed in the prior slide, there's a couple here of microscopes. One, a digital scope, which is really good for storing traces. Another, a 200 power microscope with a built-in safety filter. Again, meeting the IEC 61300 standard for performance. And good documentation. I just can't say enough about the importance of documentation. So I ran a little long here, but it is question-answer time. So let's pull these up so we can take a look at what we have here. And just waiting here. Got a little latency on the system here, and that. Okay, so when inserting a connectorized optical splitter, would you add 1 dB for your insertion loss calculation for the 2 connections? Absolutely, because it's a sum of the amount of connections in the span. So you would have, the theoretical component loss, a 1/32 splitter would be 15.8 dB is the average for a 1/32, and you have the additional connections and that. So remember, it's a full connection though. That means mated to mated. So if the connectorized splitter had a plug on one end and a plug on the other, that's not 2 connections. It's only when they're fully mated. So the 2 plugs would be half a connection each, so it would be 0.5 dB versus the 1. My email address, in case we run out of time here and people have very specific questions, is larry@lightbrigade.com. So let's see what, so how significant is the RFTS market worldwide for fiber to the home compared to traditional testing and fault finding? And that, so remote fiber test systems, so it's a case of it's a numbers game, and that the traditional point-to-point test set is the dominant type of testing that takes place in the industry. There's much more of those out. As we go to fiber to the home, as the numbers are increasing, we're seeing more specialized equipment, and it's getting far easier, and the documentation provided is getting better. So you really need to keep current with your test equipment suppliers, and if you're going to be buying new capital equipment, take a look at what you really need for your test, and find the right product that best meets your applications. And we have a question on how far can an OTDR see. It depends on the dynamic range of the OTDR. If you want, I can address that independently because that can be quite a complex question. But if you want to talk 100 kilometers, very easy. When we talk oceanic spans where we use coherent OTDRs, you can go much longer distances, but it is a question probably better addressed offline. Again, Larry at lightbrigade.com, and I'll get back to you. So at this point, we've come to the end of our timeline that we have. We do have another webinar on December 18th, and it's going to address fiber and cable management products. And they're very much in transition. There's a lot of really neat products out there and a lot of new types. So I really hope that you dial in next month. And everybody, have a great weekend coming up, and take care. And we look forward to hearing from you. Take care.